I do this using JPDM, and so you can then, we could even do that. A couple little tricks in JPDM that will help with this. So there we go, there's JPDM. And then let's see, I gotta load. I should have done this first, sorry about that, but let's see if I can edit that out. So there we go. So I loaded in the high-res dim, and and so you want to do this with both the low-res and the high-res. But I'll just focus in here on the high-res. So this is already a flat process dim. I want to focus in on this one to show you a couple different things. But first, let's discuss the flow. So something that can be useful is to have your QGIS or ArcPro, whatever you're using, available. And to get these flow path data, you're going to have your DEM. It's going to be a flat process DEM. It needs to be processed first for both your low-res and your high-res setups. Then you're going to have your flow paths. If you're just flat processing, this is just going to pop up. Otherwise, you need to then determine your flow path if you're reloading flat process DEM. And then what you can do is save your flow accumulation data as an ASCII grid, or you could even delineate to the points that you care about and save it as a delineated ASCII grid. Then everything on the outside will be no data. But either way, you want the flow paths for the areas that you care about. And then when you're so then you can do this one of two ways. Either you load the data, you load that flow accumulation map into QGIS, and then you'd end up with something like this. Or, well, let's just go with that for a minute. And then what you do is you visually decide that, like, well, I want to work in this area, and I like this little crook, this little bend right here in the river. That's a good focal point that I can remember. Then over in this data, you find where that location is. So it's like right here. This would actually be a pretty good spot too, because this is actually, I've been in this area. There's a roadway here and a bridge going over the system. Actually, I think it's here. I'd probably check this in Google Maps. I can't remember the bridge, this roadway in the bridge, or if it's this one of these. That doesn't look like it lines up right. I think it's this one. But so this might be, if this is the bridge location, that'd be a nice location to work with too. So you have this landmark. But there's this little tiny crook in the river. It's probably hard to see. So I'm going to zoom in. There we go. So right here, this little bend in the river system. And so you pick one of these cells here, maybe like right before, it's nice to have this long line. I just pick the last cell to the west, set that as my primary outlet, and now I have 690, 360. And I also have an I index for that location. And so then you want to keep that in mind, probably jot that down. And so that's going to be for this location right here. I don't know if actually, okay, that could work. So then at my low-res simulation, I'll do the exact same thing. So I'd load in my total upstream river contribution, which is this flow path here, and load that into JPDM, and then find this pixel in that setup, and then jot down its XY I index position. So that way you have both of them. And really, you ultimately really want this I index. That's going to be really the key. You need to have these I values. And they, mathematically correspond. This is a linear index of the XY. So a key note here with these setups is that they're very manual. They are fit to your data. So if you change your upstream contribution in any way, you change your map, you have different cell dimensions or something like that, then you need to redo these steps to update your I position. If you change the downstream, for some reason, let's say in this downstream, my upstream is fine, but for some reason I now want to represent over here. Well, just doing that, just going from here to here, changes everything. if I change my map dimensions, make it bigger or smaller, that changes everything. So these I indexes are fixed to the spatial data for the setup at both the low res and the high res. The flow results are all going to be representative of these setups, and so if you change anything, then you have to then re-go through all these steps and and adjust all of that information. So where does that information go though? Let's see. Is this here we go. I think this is it. So this information ends up going into a relocation manifest, which I'll show here in a minute. And that relocation manifest is going to have those I index positions from each map, from the low res feeding into the high res. And then it's also going to have a folder path, which that's what this represents as one example. So what happens here is you run your, in this example, the low res Tolt River, and then you collect this data only from those results. And so this would this actually, sorry, this says Snoqualmie, but these data here are actually, Snoqualmie is a much larger area, and so these data actually here specifically are the Tolt. And so this is my cell data writer from my setup from my Tolt simulation. This was ran under VELMA Parallel, so automatically it was tagged with this DLN writer. Otherwise though, if you're running VELMA like standard, then JVELMA from like a GUI, then you would create a cell data writer at your port point, and that would be the same location that we're talking about here. So you could create a cell data writer for this location here, and then that information would then get output with the name that is whatever you call your cell data writer. But in any case, these are going to represent the daily results coming from that location. And then you're going to have the summary information and some of the other information about the setup. So these are all provided in the VELMA simulation. They are just going to be in your output results from your low-res upstream, in this case Tolt. And then you're going to create this relocation manifest file, which, do I have that up? Let's see. So actually I'll show you this here so you can see for the two different setups we have some folders that have Snoqualmie but other ones that have only Tolt. And then so here are the data for a different Tolt setup, 30 meter. So that's the other thing here that's important. Some of my setups are from 90 meter data, others are from 30 meter. But here again, this highlights exactly what I was talking about though. You're going to have, actually, I was hoping that would be, there we go. So these data, again, just like over here, these all come from the upstream, typically lower resolution setup. And then once you have those, then you create this relocation manifest file, which is pretty simple, but key for this all working. And so you have your I index position from, so this is from the upstream, and I'm just going to say upstream. We keep saying lower res because that's why we would do this, but it technically wouldn't have to be. The resolution doesn't matter. This all works because VELMA works with all of the units regarding flow in millimeters per meter squared daily, and so we can scale up and down, and the data is fine. And so that's why this is able to work. And so this is the upstream. So this, well, I will put in here. So in this example, this is my Tolt 30 meter or 90 meter, depending on which data set I'm using. But this is my upstream low-res contribution. This is the I index position at that bridge location, theoretically. So at this location here that we were, whoop, sorry about that. At this location here, the low res. This is the big black, or the big red boxes. And then this is then my high res 3 meter, in my example at least. So this is the I index position in that same map, but these data. So focusing on this 3 meter high res pixel. And so then, once you have that manifest file, relocation manifest file set up, you're going to have your I index coming low res to high res, and then this is it has to be a full folder path, fully qualified, to the location of the data from the low res setup. So fully qualified path to these data. The relocation manifest file does not need to be in the same location. Actually, I often do not. I did early on. I think this is when I was a little rusty on how to do this. But now I keep them in other places. I keep the data. You want to keep them generally in the same place, but anymore what I do, you can see there's several relocation manifest files here, at least these ones. And we normally name them under this setup, starting with relocation manifest, so it's very clear what these CSV files are. They need to be a CSV file. That's another key point. So I'm manipulating this in Excel, but ultimately you're just going to have a row with your upstream outflow location, same location that is now your contribution upstream into typically the higher res run, and then the fully qualified folder path to this location. And so if you move the data around, you need to come back into this manifest file, and you need to change this to map that corresponding location correctly so that Velma knows where to look for this data. And you can also, I'm going to delete this now because you would not want that there. You would just want your three columns of data. But then in the example where I have the tolt coming in, but also the Snoqualmie flowing north from that large area to the south of the Carnation floodplain, then I would just have a second one. And so in that case, I would have a tolt simulation with flow results, and I could have a Snoqualmie simulation with flow results. And that would be in the example where I would have data flowing in through this area. That's all. And if you have more, you can have as many as you want, so long as the data is complete, the timelines all match, you've resolved the I index positions from one simulation to the next. You can have as many contributing inputs as you need to represent your watershed. So the key, though, the transfer of information from one simulation to the other has to fall along a flow path.